You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast. I have Beau Jarvis, the CEO of Phase 4. We're going to be talking about new developments in space exploration. So, Beau, thanks for coming.
Yeah, good to be with you, Richard.
Tell me a little bit about Phase 4. What's the what are the first three phases, and where did the name come from, and what's the premise of the company?
Yeah, it's a bit of a planned word. So really the reason why we call the company Phase 4 is that we build propulsion systems for satellites that generate propulsion by creating plasma. And of course, for those in your audience that may have had rudimentary physics, they may have heard that there are four phases of matter, right? You've got your gas, your liquid, your solid. But I think most of us, myself included, up until recently, didn't really think about plasma. So plasma is the fourth state of matter. That's what we use to create satellite engines effectively.
Yeah, why would plasma be how is it used in propulsion?
Yeah, if you take a step back, there's generally two types of propulsion, and most folks are familiar with what we call chemical propulsion. So that's the fiery type of propulsion that you see coming out of the back end of a rocket as it's launched from Earth to deliver things into space. But the other type of propulsion is called electric propulsion, and that's more commonly used, or pretty much only used in space. That is used where you take a gas, something like a noble gas like xenon or krypton or argon. You excite that gas with electromagnetic waves. That gas then becomes highly ionized and turns into a plasma. And plasmas want to kind of move together. So you can direct the plasma out of the back end of the propulsion system by using an electric or electromagnetic field, and then that allows your spacecraft to move around in orbit in space. So it's a lower thrust, obviously, than you get with chemical propulsion, but when you're up in space, you don't have the pull of gravity as much as you do on Earth, and it's a much more efficient system. So it uses, think of it as a higher miles per gallon system than a chemical propulsion system.
You're creating charges, a charged gas essentially, like a plasma, and then the charge separation in a field is what causes the propulsion.
Mm-hmm. Yeah, exactly. Yeah, so typically if I'm sure a lot of folks see a rocket and they see the physical nozzle of the chemical propulsion system. We actually use a magnetic nozzle, so basically directing those charged particles the direction that we want the spacecraft to travel. So basically directing them at the back, that makes the spacecraft move the opposite direction.
How much more efficient is this method of propulsion? Like how, if you compare it to other methods of propulsion, I don't know if you should say miles per gallon. There is no such a thing, but what's the metric that talks about efficiency?
Yeah, there's a few metrics that people use, and generally it is thrust. That's basically the strength of propulsion. So obviously a chemical rocket engine has much higher thrust than a electric satellite propulsion system does. But then there is thrust efficiency. That's really how much thrust can you generate per unit of input. So it's either electric power in coupled with the amount of propellant in. So it gets fairly complicated pretty quickly, but generally the idea with an electric propulsion system for a satellite is you want to have enough thrust to move something around, the way that it will meet your mission requirements. But you also want to have enough efficiency so that if your satellite, let's say, you need it to last 5 years or 10 years or 20 years, you need to have a high enough efficiency level so that your fuel that you've got on board your satellite lasts for the entirety of the mission.
And what is the fuel? What's the source of the fuel?
Yeah, so traditionally for large satellites, so the satellites that a lot of us probably don't think of oftentimes, but are when we're watching television or we're seeing news broadcasts from the other side of the world, those have been what are called geocomsats. So they're large telecommunication satellites that are in a geostationary orbit. Those typically, were in orbit, 10, 15, or 20 years. And a lot of times they're using electric propulsion systems with something called a Hall thruster that was actually developed in the 1950s, right in the middle of the Cold War. It was developed in the Soviet Union. And that takes xenon, which is one of the noble gases. So it's inert gas, so pretty safe to handle, but can be a very densely packed gas. And that is historically really the only fuel for electric satellite propulsion. Really what we're doing differently is we're still able to generate a plasma, just like legacy systems are, but we can use any neutral gas input. So we can use xenon, we can use really any noble gas, so argon or krypton, but we can also use novel propellants, things like water vapor, things like air, things like methane. And that's where it gets really interesting from a infrastructure and space standpoint. Right. So rather than carry an earthbound fuel like xenon all the way out to the moon, if you're trying to build communications infrastructure around the moon, for example, or further out something around Mars, you can actually use locally available fuels to power your infrastructure. And that could be, water vapor for spacecraft around the moon. That could be methane for spacecraft around Mars. So that's really the major difference between legacy electric propulsion and what Phase 4 is building, is the agnosticism to fuel inputs.
Is there just too few particles in space in most places to be able to use that as a fuel? I mean, it's called vacuum, but there are clouds of gas that are in the way of an object's journey that it could use and harvest, or is that too way out?
Yeah. That's probably a little bit further out there. I don't think it's outside of the realm of possibility. I think more realistically, what you're looking at is things that are readily available. So let's say, if we flash forward a few years and our friends at Blue Origin have built up some level of colony on the moon, for example, they could extract water vapor from some of the ice trapped in the moon and, basically make a fuel depot there. Or on the Mars, the same thing. The Martian atmosphere, has a lot of methane in it. But I think further out, as you mentioned, there is this concept where you have something called a harvester. The spacecraft could basically be designed to take in a specific type of gas, or really any gas, right, and convert that into fuel. That concept actually has been started to be developed with the European Space Agency, not necessarily for deep space missions, but for very low altitude missions. So if you're at what we call in a very low Earth orbit, that's anywhere from like 200 to 300 kilometers above the Earth, you can orbit there, but the problem is gravity has a stronger pull there. So if you're orbiting there, your satellite comes down very, very quickly just because it gets pulled back into the atmosphere. But if there is a concept out there that if you had something akin to a turbo, basically something that will allow you to suck in air, and you had a propulsion system that can convert that air into plasma, like an electric propulsion system traditionally does, then you could effectively orbit as long as you wanted, right? Because there's an unlimited supply of things like nitrogen at that level of the atmosphere. So that concept exists. Again, there hasn't really been a technology up to this point that has been able to leverage, different types of inputs to create thrust. So that's something that we're actually quite excited about.
Yeah, I wonder if if you had well, this could work for other planets too, or I guess the moon. If you could make it such that the craft wouldn't have to land, but could go to a lower orbit. Use the planet's gravity or the object's gravity to pull it into a lower orbit where there was enough of some material, methane or whatever it was, harvest that, and then leave the planet with that extra fuel without having to land. That might be an interesting way to do things.
Yeah, exactly. I think obviously that there's some there's some technology that has to be developed to get to that point, but again, I don't think it's out of the realm of the possibility. And one of the exciting things of what's going on in space right now is that I think really over the next decade you'll see a lot of these things that most of us thought was purely science fiction start to take shape and come to reality. So that's it. If you're interested in space, it's about as exciting as it can be in terms of time.
Well, what are some of those things? What do you see that's coming in the near future, 5, 10
Yeah,
years?
yeah. I mean, I think if you look at just over the next, let's say, 5 to 10 years, and we just stick on Earth for a moment. I think some of the really interesting things that will require lots of revolutions in technology. So I think that's where we'll see lots of things change very quickly. Are in something called these megaconstellations, and that's a term that has been developed to describe constellations of satellites that number in the hundreds or in some cases in the thousands. And really what you're starting to see is new companies, if you've ever heard of a company called OneWeb, or existing space companies like SpaceX, their concept of basically having space delivered internet for the entire planet. So basically, no matter where you are in the planet, you could get the internet. Now, there's probably debates as to whether that's a good or a bad thing, but really, essentially developing these large constellations that orbit the Earth that bring telecommunications down very, very close, so you have lower latency and much broader coverage. And you're actually starting to see larger telecommunications companies look at that and think about, okay, rather than one very large school bus size satellite that sits in geostationary orbit for 20 plus years, we could build hundreds of satellites that orbit much closer to the Earth and replace them every 4 to 6 years. Therefore, we're not going to get left behind from a technological perspective. So you're basically going to see effectively mass manufacturing of satellites start to take shape as soon as this year. And then what that means for other parts of the infrastructure that has to go in place, that's why we exist, right? Is we represent something that can be manufactured at scale, and again, that can use various types of fuels to power different satellites. So that's one of the things that I think maybe a lot of kind of your layperson that's not in the space industry might not be aware of, but that is happening right now. That we'll start to see hundreds of satellites launched on an annual basis. Really, if you look at now, I think the last I saw, the number of objects orbiting the Earth in low Earth orbit, I think is around 1,700, if I'm not mistaken. But just the number of licenses that have been granted to companies like SpaceX and OneWeb over the next decade, you're going to see about 20,000 satellites being launched and orbiting the Earth. So we're looking, at such a step change in terms of things going up and things orbiting the Earth. And then if you start to look, out beyond the Earth, you see, people talking about how do we develop this lunar gateway? How do we get a spacecraft to Mars and then get it back again? And what does that mean for, infrastructure between the Earth and Mars? So I think a lot of the enabling technologies you'll start to see are going to be pretty interesting just to see how that plays out. And I think the compressed time horizons from, thinking this is going to take 20 or 30 years to happen, things is probably going to happen in a much faster pace than a lot of us are used to. So those are types of things I'm interested in seeing.
Well, what's the thinking? What's the purpose of having, normal transit between us and the moon or us and Mars?
I think there's from a scientific standpoint, there's probably a lot of knowledge that's locked up, between here and the moon and here in the Mars that we just don't know about. Things that could enable deeper space exploration. I think there is that inherent, need to explore and need to discover. That is, something that if you look throughout history, that's just, why did you have all these people kind of sailing around the ocean? And yes, there are economic incentives, of course, but I think there's also really interesting scientific questions that can be answered by doing more research into space. And then I think, there is the probably, in my opinion, there's some debate as to, is there purely a commercial reason to go all the way out to Mars? And if you look at it from a, maybe a purely commercial standpoint, and, there's probably, precious minerals, those types of things that exist in space at quantities much greater than they exist on Earth. So, even at that basic level, there's probably some justification from a commercial standpoint there.
So your goal is to I mean, where do you want to make an impact with propulsion? You said you want to be able to have your system robust enough that it can use multiple different inputs, such as methane or water vapor or other stuff all in one go, or where's the leverage that you're working on?
Yeah, really, the vision we have for the company is that we see a future in which all of the mobility in space, so basically, any spacecraft or satellite that's actively orbiting another celestial body or providing some level of infrastructure in terms of communications or observation, it is powered by phase 4 technology. And the reason we think that that's actually a realistic vision is the hallmarks of our technology is that it's fundamentally a much less expensive type of system to build, and the fact that we're not tied to a single propellant input makes it much more flexible. And again, that contributes both to the lower cost, but also to the complexity in terms of different types of missions that a satellite could take using our technology. So for me, that's exciting. There's the mass manufactured angle where we're going to have to support tens of thousands of satellites, but there's also the deep space or off Earth exploration angle where we could be the technology that's used to help build the infrastructure in deep space, and that's pretty exciting.
Quick question: when you leave Earth's orbit, you're headed, let's say, towards the moon. You're in space and vacuum, I guess they call it. How much propulsion is needed? Do you need just a tiny bit, and the spacecraft will just keep going and going and going?
Yeah, it's really, and I'm not a huge fan of these types of answers, but it's really mission specific. So what does that mean? There are some satellites that they don't need to move terribly fast or terribly often, so they could have a low thrust system, with a small amount of propulsion because they don't really need to use it very much. Or there are satellites maybe that are, or probably this will become increasingly more common, that are orbiting in low Earth orbit, where they need to be able to move reasonably quickly because there's so much stuff in that orbit. So then they would need to look at a higher thrust system where they would probably use more fuel. So that could effectively shorten the lifetime of that particular satellite, or they would need to look at, other technologies. There's other concepts out there where you actually have a dual propulsion satellite. One is a chemical propulsion system, which basically is kind of like the emergency turbo boost that gets you out of the way of something that's coming at you very quickly. And hopefully you don't have to use that very often, but if you're in a crowded orbit, you may have to use it. But then you have your more efficient lower thrust electric propulsion system that lets you do, the typical things that a satellite that has to do, like, keep its orbit the same as it goes around, maintain its position if it's in a network of satellites, those types of things.
Right, but again, going through space between bodies, here to the moon, here to Mars, etc. I guess would you just need, again, a very tiny amount of propulsion if you were happy to go there slowly and steadily?
Yeah, exactly. So there's, there are some of the some of the scientific spacecraft that we've heard of, like Bepi Colombo, and Marco, and more recently Hayabusa 2, which is a Japanese satellite that was exploring meteors. Most of those use electric propulsion because they're not in a hurry necessarily to get someplace, right? So they can take a bit of time. I would think on manned missions, for example, what SpaceX is building in their Starship, that the need is basically to minimize the time, right? So they're building a very large spacecraft that can take a lot of fuel on board and get someplace faster with a chemical propulsion system. So again, I think it goes back to what you're wanting to do. But if you're purely out there in the cosmos exploring, and you just want your satellite, for example, to keep going and going and going, and you probably use a very highly efficient propulsion system like an electric propulsion system.
Okay, well, very good. So what's the best way for folks to learn more about Phase 4 and these types of initiatives in general? What do you recommend people do to learn more?
Yeah, I mean, we're in the process of building our first product, and we're going to make deliveries to our customers this summer. So we actually have a lot going on. We're pretty visible on social media, on Twitter, on LinkedIn. So if people want to know specifically what Phase 4 is doing, we're pretty easy to find. I think generally speaking, if someone was interested in kind of all aspects of space, like commercial space, NASA related or government related missions, there's a lot of really good outlets out there. One that I look at on a daily basis is Space News. It has a pretty easy to follow news feed, but it's very diverse. So if you're just someone who wants to know what's going on, both from a commercial and a scientific standpoint, that's probably a really good place to visit and or to follow.
Okay. Well, very good. Well, Beau, I appreciate you coming on the podcast. Thanks for being here.
Yeah, good talking with you, Richard. Thanks a lot.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.